Yes, madam, we are live in both Zoom and YouTube. If any questions comes in YouTube, I'll just copy the questions and paste it in the chat box, Zoom chat.
Thank you so much. Yeah. I think I've seen Abhilasha there online. So, do you have any queries? Please unmute yourself and then ask me.
Okay. Miss Abhilasha, please unmute yourself and keep the mic bit higher and then please mention.
If you have a mic problem, you can post it in the chat box also your question. So I'll be answering it.
I have few clarifications in assignment 4, ma'am. Miss Abhilasha, your voice is very feeble. We could not hear anything.
Assignment 4, which part of the assignment 4 you have the problem? You want me to project the assignment 4? So that we have the assignment 4, no? Okay. Is it the complete assignment 4 you have a problem or any particular thing?
Just a minute, I'll post it. Just a minute.
Okay, question number 8, what she is putting it. This assignment is already answered, correct?
Ma'am, can you see the question now? Question 8. Last date is tomorrow. So this is the question 8. Given f of k is equal to 5 plus 2 cos pi by 2k minus 90 degree plus 3 cos pi k and n is equal to 4. Value of f of k for k is equal to 0. 0 to 3 are so and so, so and so, so and so. And Miss Abhilasha, can you please, what is your question? On question 8, what is your question?
To give you a clue, actually, you can put k is equal to 0 to 3, what it has been asked, okay? So you can find out your f of k values.
Okay. Any further query, Miss Abhilasha?
I thought it is, no, it is 0 to 3, sorry. It is dot, one more dot might have missed out. In the thing, 0 dot 3 it is, or 0 to 3. As you have put it, it is correct. Any other this thing? Doubt you have it? Oh, sorry about it. There should have been 2 dots, I think. So 0 dot 3. Yeah, fine.
There are 2 dots, ma'am, in that.
2 dots are there. Okay.
Yeah.
But what she has put it as 0.3. That's why I thought, okay. Any other queries? As you can see, the can we have the first week thing? Yeah, so we have done introduction to RTSP in signal processing. So something basic number system, because when we're implementing on DSP, we should know the number system, how the architecture is defined. So based on it, what we have to use, able to download either 6713 board, what you can use it, or a simulator. I think 5.0 simulator CCS has been shared. So you can work initial, all the assignments, basically, whatever it has been said in the class. And then try on your own different coding and other things for applications. Only for the real-time part of it, so you should have the board, basically input and output, audio codec, what it uses, the thing, if you are working in the speech processing or audio processing. So if it is image, the thing what you want to look at it, then you have to store it in a file, and then you have to run the algorithms in your Code Composer Studio. And then you can take out the data, and then you may have to plot it in MATLAB. So most of the experiments you should be able to do it in MATLAB. The open source is given. And if you want to try the same thing using is your Code Composer Studio, you have to write it in C or C++ code. Okay. So for this DSK boards, we don't have support of Python code actually. So it has to be C or C++ code. And how the architecture takes care of your addition and multiplication. So you can, I think in one of the assignments I have given how you can check your coding computation time. Okay, so that also can be used. And how all this barrel shifter for loading and other thing has been incorporated within DSP processor. So go to the next addressing next week thing. So as you can see, which are the experiments we can do it in a board basically, or using MATLAB also. So you have seen FIR filters, how by pipelining and parallelism can one way help in speed up your algorithm. But if you are looking at from the point of view of energy, basically, that is power saving, then how you can use them at the same clock speed, how you can achieve at a lower voltage, you can run your own hardware. If you are designing in your FPGA, so you can run at lower, I'll put it as voltage, and then you will be getting your output at the same clock speed. This is one of the thing. That is what it says, real-time constraints when you are designing your own hardware. Here we are using a inbuilt hardware of DSP processor, which is given by TI in this case, and we are working on the real-time part of it. Here also you have a constraints when you are designing your when you have your own constraint on real time, what I put it as within one clock cycle, you have to get your output. So which is going to involve, as I mentioned, your computation time as well as your IO bandwidth. Basically, all this has to be taken into account. So your computation time has to be within 40% what we usually assume, because the rest of the time takes for your IO settling and loading and then outputting the things. So in this case, we went with the simple FIR filters. So we said it is a linear phase filter. How it is linear phase, we have taken an example of low pass filter and then one high pass filter and this defined. So the other things you can derive for bandwidth, band pass and then band stop filters also. So why we the one of the thing is design part of it, or getting the coefficients, we do it from MATLAB, and then we'll be using those coefficients in our DSP processor, and then we'll be running our code. So either filters are usually in the applications of modifying the input signal, or you want to eliminate certain frequencies of, that is what the application is. One of the thing is, if it is a low pass filter, we know that we'll be allowing some frequency which are of importance to us, and rest of the higher frequencies we are going to eliminate it, which is equivalent to noise removal, what I can put it. So that is one thing. And then we have worked out one or two problems from Keshapari. The book is downloadable. So if you want, you can download the book, and then you will have problems at the end of the, here only chapter 3, what I have considered for the pipelining and parallel processing, and then how one wants to design in hardware. What are the cases one can take it, because we know that multiplier is going to be when we are using that is booth multiplier, so it will take little more time than my adder. So how will be taking care of capacitance effect and other things, charging and discharging part of it, what we consider it, and one can design with it. So this is the second week thing what you have looked at it. In a summary, what I am putting it. So the third week is all of us know FIR and IR filters. We have done the lab experiments. So the filtering is usually there are 3 ways of generating your own what I'll put it as input. One is sine wave generation. You can use the the function to generate your sine component, multiple sine waves what you can generate, and then see that how you can eliminate in your hardware basically, or simulator what you are using it. And then any of the filters, low pass filter or high pass or band pass or band stop filter, you can look at it. Most of the time band pass filter, band stop, we use it for I'll call it as eliminating certain line frequencies. So if you consider our India, it is 50 hertz. So in the ECG signal or something, this comes as a noise which has to be eliminated. So we use for it. and then that is how you will be generating one way of sign generation. The second way of is using tables. So you generate the values using MATLAB and then put it in a table, and then you can use it for your filtering basically. So, and then output you will be seeing it in plotting in the Code Composer Studio itself. So the third method of it, in this case, we are using the IR filter. So all of us know that it is, if you remove your input also, output basically will be continuously coming out in IR filters if we use them in an oscillatory mode. So we give initial conditions basically, and then we allow the IR filter to generate. So we have checked that thing using sine wave generation, so that whatever frequency I want to generate the thing, I'll be giving the coefficients for it, A and B coefficients, if you have seen the equation, and then the filter is going to oscillate and give me a sine wave through that. So this is the best way of doing it in hardware, because it's going to consume very less time. Whereas using a math function, you know that I had to use the libraries, which is completely has to be loaded. It is not only for one function what it has. And even using tables will be, if it is a long data, if you want to have it, then what is it is your memory is going to be occupied, or you may overflow in that case also. For real time, it is better to have IR filter designed for generating sine waves, so that I can be getting it continuously. So as we know that FIR filter is stable, whereas IR filter can become unstable if you have not designed it properly. So we have seen quantization effects, what all we had it. When we use it in the direct form, how when we do coefficient quantization, how the system can become unstable. And then the realization part of it is basically we go for the biquad sections, so that any disturbance in the quantization, only that particular what we'll call it as block will get affected, not the complete block in the direct form one implementation. So for this is for the stability part of it. And then we have to use Z transform here basically, so which is derived from Laplace transform. And one of the important one has to keep it in mind when you are designing your IR filters. We know that it is not a linear phase. So we have a phase is going to be different for different frequencies in the same signal basically, whereas it is constant in FIR filter. So if you are allowed to do this phase, whatever I'll call it as nonlinear phase, then you can, with the lower coefficients, you can generate your IR filters, so that your storage and then computation time will be less in your hardware. Same thing, if you are implementing FIR, it is going to be little more. So the next one comes as impulse invariance mapping or bilinear mapping. So when you are sure of your cutoff frequency, you have taken care of not any aliasing is going to happen, then you can have the impulse invariance mapping, which is easier to design basically. But if you are not sure, because it is in the always, I think even in the class I have mentioned that the stop band frequency in most of the filters which has to be met, okay, at least we can allow little on the pass band, but stop band cutoff should be exact, so that if we little bit deviate also, we may have higher frequencies creeping in the pass band region. So it may cause instability to the system, or it can have a aliasing effect in the frequencies. So this one has to take care of it. So whereas we can go for the bilinear mapping, only the thing is we have to do the compensation there, whatever we have taken care of in designing it. So how we do the design, this also actually earlier it used to be hard to design an IR filter, which was done using analog domain, because we know that it has a heritage of more than 125 years of their existence and other things. So it is completely designed in analog domain. So usually we design in analog domain, either using a Butterworth, elliptic, or Chebyshev filter. So Butterworth will have the highest frequency, coefficients basically, compared to other two. Elliptic will have the least. But the problem is you will be allowing ripple in elliptic filter, both in passband and then stop band. Mostly we may not be using it, either Chebyshev 1 or 2. So one of the things, Chebyshev 1, which has a flat response in, I'll put it as stop band. So we prefer that because I don't want any aliasing to happen. So the other one is the errors we said. There are 4 stages of errors. One is ADC quantization, because first from analog domain we have to convert it into digital domain. So we'll be using the ADCs basically. So there itself we'll have the quantization. So how sigma delta can give us high rate sampling, so that we can avoid aliasing filter in the analog domain. So that is what we have seen the thing. And then the second stage of error will be when we are using the DSP processor. So based on whatever the design, direct form or indirect form, and then how we represent our coefficients, because their coefficient quantization is going to happen. This is the second error what we have to take care of it. And then the third error is a math error. Basically, we'll be doing multiply and accumulation in the hardware. So I know that my number system does not provide me to extend beyond in these DSP processor, what we are considering, more than 16 bit. So if I increase my whatever output, then I'll be extending my memory, as well as what we consider it as it goes on building up forever. So to restrict it, we have to what I'll call it as restricted to 16-bit output, also from 32-bit to 16-bit. There also your math error will be coming into picture. The last stage of it is because I have to do digital to analog conversion. So there also DAC will be giving error, basically approximately what we'll be mapping it. So considering all this, depending on the application, so you have to see what kind of filter, what kind of hardware, and then how many number of bits what you need it. So whether you can mostly use these basic boards for your own application. Most of the audio and speech processing, it is enough to have 16-bit processors. So the next one is how to avoid this quantization, because overflow is going to happen. So how you can do from stage to stage, you may have the overflow. Then each stage you may have to do the basically avoid the overflow. For that we have to do the scaling. So which are the 3 scalings we considered is L1, L2, and L infinity norm. Okay. So these are the 3 ones. L infinity, we know that if it is a input is a sine wave, and then how does it can be scaled to the maximum, and then so that we'll not have any overflow at the output, what we have seen the thing. So it is very difficult to use in some cases. Only in term of sine wave it can be defined. And then L1 is the maximum value you will be taking it, and then you can divide all the inputs so that it is scaled. So if there is a small value in your input, if it's almost it may go to 0. So then you are overscaling in that case. So we said it is L2 norm. Depending on the coefficients, A1 and A2 coefficients, we can define what should be the scaling thing, which comes in between. So most of the cases L2 norm works. So if where there is a problem, then we may have to go to either L1 norm or for scaling, or L infinity, depending on it. So we have seen using MATLAB how you can define your using a filter design toolbox, and you can generate your low pass filter, high pass filter, and then see their characteristics, whether you want the linear or non-linear, you can accept, and then whether it is stable filter in case of IR filter using MATLAB. So once you get the coefficient, so you'll be using in your Code Composer Studio. So how, as a lab session says, as a resonator, I said we can have it in the oscillation mode to then generate sine wave. Yeah, go to the next slide. So in the week 4, earlier it was a FTA toolbox was used for FIR and IR filter design using MATLAB. So now they call it as a filter design toolbox only. So you should be comfortable if you are using a old version or new version. They'll give you what toolbox has to be used, and then how you will be reading the data, and then how will you be outputting it. So as a lab, think audio output just to play around if you are comfortable with some music or whatever may be the thing. So here, how you can synthesize your music. So we know the frequencies of it, either using a sine wave, you can generate multiple frequencies of this, whatever octave you are going to select it. It can be 240 hertz or 400 hertz can be the base frequencies you can select, and at what you call it as approximately 32 hertz interval, you can generate these notes, which is going to give you a music synthesis, basically Sarigama Padanisa. So that is what is shown in this. So that is one way of doing it in MATLAB, to verify that our frequencies what generate is giving me this music note. The same thing what you can use using a C code, do it in the DSP processor board. So, and then how you effect of quantization on center frequency, what we did a little bit of problem solving. So one can even see using, you can use MATLAB to look at this quantization effects and other things by selecting various quantization levels. Okay, 8-bit quantization or 3-bit quantization or 5-bit or 16-bit. So whatever problems you have worked out, you can put it in MATLAB and then test it, basically. So the next one is how stability, already I have mentioned it, and then how you can get your desired frequency response, addition, and then overflow errors. We have seen that these norms, how you can provide it. One has to observe when you are using the toolbox in MATLAB, when you generate a IR filter, this thing coefficients, you will be getting stage wise, basically. So if you give a stability as a constraint, then you will be getting a stable filter coefficients, what it is going to generate, and then from there, if you want to have it for TI processor thing, you can select there. I want it in the fixed point also. It will give you the coefficients there. So which you can use it in your Code Composer Studio. So the next one is we started with discrete Fourier transform here. So how we can use butterfly structure basically to define our, butterfly structure will be coming for FFT. So why we want DFT, that is one thing. So as we know, DTFT is a discrete time Fourier transform. So what do we mean by that? It is discrete in amplitude, but frequency it is continuous in DTFT. But when I'm representing in my hardware, I cannot have any continuous part of it coming into picture. Then what we do is I want both it should be discrete in amplitude as well as frequency. For that, we do go for discrete Fourier transform. First of all, why do have to go into the frequency domain? That I've explained in the class also. So that is as you generate your sine wave, you can see that what are the frequencies. If you know, if you have generated yourself by specifying the frequencies, you know what are the frequency component present in your sine wave. So if somebody gives you a sine wave, I don't know what are the frequency component and what I'm going to do with it. Which one is relevant for me, and then which one is relevant for others. It is depends on some of the applications. How I'm going to see what are the components present in it. So from one time domain, if I go into the frequency domain, so the frequency components I'll be getting from the input data, which I'll be using it for my application. One of the thing is circular convolution. So some examples we took it, some properties also we have seen from how we will be going from analog to digital, frequency domain. And then here linear convolution, what it becomes a circular convolution in Fourier transform. And if you want to do the linear convolution, then your length have to be adjusted to, if L is the input length and M is the coefficient other sequence length, then the length of both of them has to be adjusted to L plus M minus 1. And if you do the convolution, then you'll be getting linear convolution using circular convolution in DFT domain. So some examples we took the thing, so you can see more examples and how you can implement them in MATLAB. It is directly, you will be giving it as DFT, you can do it, or FFT. What you DFT you have to give, then n is equal to 0, so e power minus j2 pi n k by n should be your equation to implement DFT directly in MATLAB. Or there is a function FFT, so that also you can use it and cross verify your results. So any doubt in this 4-week thing? I think, hope I've covered everything. I've answered whatever question was asked. So anyone else, I think one more has joined. So if you have a question, if you can unmute and then ask me, I'll be able to answer. Or even in this, any doubt is there till 4 weeks? Whatever concept you have not understood or you need more explanation. Hold on, I have to open it. Oh yeah, if you people don't have any queries, thanks for joining this online meet and then taking up the course basically. Hope you are enjoying. So thank you.
Shall I end for everyone, madam, then?
Yes. Something, what is it? What is it? Okay. Thank you, Abhilasha.
Okay,
Yeah,
madam.
you can end.
I'll
Yeah.
make end for everyone, and still there
Yes.
is no question in YouTube also.
Okay. Okay. Thank you. Thank you
Thank you,
for
ma'am.
sparing your